Hi everyone, my name is Daniele Regoli and I'm going to present Bias on Demand, a modeling framework that generates synthetic data with bias. This is a joint work with Joachim Baumann from the University of Zurich and my colleagues in Intesa San Paolo, Alessandro Castelnovo, Riccardo Crupi and Nicole Inverardi. In a nutshell, in the paper we propose a simple system of stochastic equations able to generate datasets, synthetic datasets with specific forms of bias. The main goal is to foster the study of fairness and bias mitigation in datasets where you can control the type of bias that you have injected in, which is rarely doable for real-world datasets. In the following, I'm going to focus a little bit on the types of bias that we are focusing on in the paper. Then I'm going to present you the synthetic data generator, so the system of equations, and then I'm discussing a little bit about the experiments. Of course, you can find much more details in the full paper, and I'm also in the end showing you the link for the GitHub repo where we put open source the toolkit. You can play with it with all the code that we've done, also for the experiments. So regarding the types of bias, let us first set the stage with some notation with variables. So with capital A, I'm denoting the sensitive attribute, will be typically for simplicity a binary variable. Then with capital R and capital Q, we denote the features relevant for the problem. For example, you can think about skills in a job application in the recruiting use case. You can think about income or financial status in a credit line use case. With capital Y, we denote the target variable as usual, the variable we want to estimate. It will be, again, for simplicity, a binary target variable, so granting or non-granting of a loan, for example. With capital P, we denote proxies for these variables. I will be clearer in a moment. So in the paper, we focus mainly on two types of bias, two classes of bias, actually, from users to data and from data to algorithm. Biases from users to data are the biases that impact the phenomenon that generate the data. So this is a simple plot to schematize what we're talking about. We talk about bias from users to data and in particular, we talk about historical bias. When we have a relevant variable R, you can think, for example, about income that is relevant for the problem. So it impacts the target variable Y, but is in some sense skewed, is impacted, is dependent on some sensitive features. So with beta, we denote the parameter by which in the generator we control the presence and the strength of bias. And with alpha, in the generator, we denote parameters that governs the strength of the dependencies between the variables. So in this case, a relevant variable is impacted by a sensitive feature. You can think, for example, as I said, income, which for social reasons, for historical reasons, are dependent, for example, on gender. So on average, women has lower income than men. It depends on the country, of course. And you can think of this as an historical bias, a form of historical or social bias. Of course, historical bias can happen on the target variable as well. And this is different from another class of biases that go from data to algorithm. So biases impacting the data collection, not the phenomenon. So in particular, in this simple plot, we schematize what we call measurement bias. So instead of accessing the real relevant variable, relevant feature R, we have access to a proxy which happens to be biased, so it happens to be impacted by a sensitive feature. You can think, for example, when you measure the IQ score to measure intelligence, maybe the IQ score may be a biased proxy for what you actually want to measure. Again, also this type of bias, measurement bias, can happen on the target variable as well. Of course, there are many other types of bias. In the paper, you can find much more details. The generator is able to generate other types of bias as well. There are nuances also in the types of bias. I leave this to the full paper. So let us talk about the synthetic data generator. As I've said, this is a system of equations. We have tried to reach a balance between simplicity of the generator itself and flexibility to accommodate several forms of bias. this sector, these three equations are the sector of the generator for the features. So we have, for example, the sensitive feature, which is simply modeled as a binary Bernoulli random variable governed by this parameter POA that controls the relative proportion of the two groups. Then we have a continuous variable, capital R, a categorical variable, capital Q. All these two variables may be impacted by historical bias, by controlling these parameters, beta of R and beta of Q. Then we have a target variable sector, which is modeled by a continuous variable S that is influenced, of course, by R and by Q, and possibly, if there is historical bias on Y, also by A, by the sensitive attribute. And for simplicity, we simply threshold this variable S in order to get a binary classification problem. We have also the sector of the generator that governs the measurement bias. So these are the two proxies, the three proxies actually, the proxy for the feature, for the relevant feature, and proxy for the target variable that may be biased if these parameters beta of M are turned on in some sense. You can also simulate the representation bias by undersampling the set A equals 1, either conditionally or not conditionally on other variables, for example, on R. So this is the generator. In the paper, you can find a lot of experiments that we've done to explain, to analyze how the generator works. Here I'm just talking briefly about the general setting of the experiments, and I'm touching upon a single outcome of a single experiment. So we generate 8 different types of bias with several scenarios. For each scenario, we generate a different dataset, a single dataset, a dataset, and on this dataset, we train a simple random forest. And then we apply mitigation strategies upon it. So what is called the fairness through unawareness mitigation strategy, that is the blinding of the model with respect to the sensitive attribute. And many post-processing techniques enforce demographic parity, enforcing true positive rate parity, and all the other error parity that you can think of. This is in general what we've done in the experiments. This is the outcome plot of a single experiment where we inject a single bias, a measurement bias on R. So we use a proxy. Instead of R, we are using a proxy, a P of R, which is dependent on capital A. The interesting outcome here is that you can see that in the unmitigated model, so the plain random forest, all the measures, all the group fairness metrics are 0. So there is no bias with respect as defined by several group fairness metrics, but there is bias if you blind the model. So this is an interesting case in which blinding the model is not useful, but it is even harmful. The explanation is very simple. The unmitigated model has access both to P of R and to capital A, and by explicitly using capital A is able to compensate the dependence that you have in P of R in order to not have an outcome that depends on capital A, depending on the sensitive attribute. This is not doable in the blinded model. Blinded model has only access to the skewed proxy, so it propagates the skewness, this dependence on the sensitive attribute on the outcome. And so you have these disparities appearing, and you have also a decreasing, as the bias increases, the strength of the bias increases, you have also a decrease in the accuracy of the model, actually. So wrapping up, our findings in the experiments empirically confirm the effectiveness of post-processing solutions, except in the generate cases that you can find in the paper. We see different trade-offs when enforcing different fairness metrics. We have seen, for example, as I've showed you right now, limitations of a blinding approach. And in general, we hope that open sourcing the toolkit and the generator will enable and foster the research on specific forms of bias. Something that we want to do that we have still not yet fully investigated is the extension of the generator to non-linear cases. The implementation of bias in the generator are almost all linear, but what happens if you have nonlinearities? Do the results that we find in the linear case generalize? Another interesting thing to do is to investigate the combinations of bias. You can find some attempts in the supplementary material of the paper, but much more can be done in order to find something interesting when you have combined biases, combined types of bias. And then, in general, we need to find other promising experiments to do in order to find interesting and useful insights. So this is all, thank you. In this repo, you can find both the package in order to install the package and to play with the generator, and also all the code that we've used to run the experiments that I discussed, and all the experiments that you can find in the paper. So I encourage you to read the paper, to read the full paper, and in particular to play with the generator in order to find interesting insights. So thank you for your attention.